As we have already seen, the densities of gases are much smaller than the densities of liquids and solids, and are easily changed by simply changing the pressure or volume of the gas you have. However, if we divide both sides of the ideal gas equation by V and by RT, we get N over V equals P over RT. While N over V is not the density, in gases the density is usually measured in grams per liter, it is something close to it, which is the concentration. We know that moles times molar mass gives grams. So, if we multiply both sides of the previous equation by molar mass, capital M, we get moles times molar mass over volume equals pressure times molar mass over RT, which reduces to mass over volume equals pressure times molar mass over R times temperature. This does give us the density, since density is mass over volume. To determine the density of a gas, then, it is only necessary to know the molar mass of the gas, the temperature, and the pressure. It is not necessary to know the volume. We can rearrange the equation to determine the molar mass of a gas from the density, pressure, and temperature. From density equals pressure times molar mass over R times temperature, we get molar mass equals density times R times temperature over pressure. It should be noted that it is not necessary to know this equation to determine the molar mass from the density, since we can choose any volume of the gas, a convenient one would be 1 liter, find the number of moles at the conditions given, and divide the mass by the number of moles. However, the equation is convenient if one is doing a lot of this type of calculation. There are 2 problems that refer to these questions on the problem sheet for this lesson. Dalton's law of partial pressures states the total pressure of a mixture of gases equals the sum of the pressures that each gas would exert if it were present alone. In other words, P total equals partial pressure of gas 1 plus partial pressure of gas 2 plus partial pressure of gas 3, and so on for however many gases are present. The idea of partial pressure makes a good deal of sense, since we know that the molecules in a gas are very far apart and have virtually no interactions with each other, even if they are the same gas. So each molecule acts as if it is alone. It is no surprise, then, that the gases act as if they are alone. The concept of partial pressure is particularly useful when dealing with collecting any gas over water, because when that happens, there is water vapor present as well as the gas in the container. To determine the pressure of the gas, we measure the total pressure, then simply subtract the vapor pressure of water at the temperature of the gas mixture. There is one problem that makes use of this idea on the problem sheet for this lesson. The mole fraction, symbol capital X, is an important concept and very useful in dealing with gases. The mole fraction of a substance Z is the fraction of all the molecules present that are Z molecules. Another way of saying this is that the mole fraction is the moles of the particular gas divided by the total number of moles of gas present. In mathematical form, we have X sub A equals moles of A over total moles present. That is N sub A over N total. For gases, the number of moles of the gas is directly proportional to the pressure if the volume and temperature are constant. We can see this in these two rearrangements of the ideal gas equation. Moles equals pressure times V over RT, and pressure equals moles times RT over V. In a mixture of gases, all the gases and the mixture itself have the same volume and temperature. So what we have is the total number of moles equals total pressure times V over RT, and moles of gas A equals partial pressure of gas A times V over RT. If we divide the right-hand equation by the left one, we get moles of gas A over the total number of moles, that is the mole fraction of gas A, equals the partial pressure of gas A over the total pressure. In other words, in any mixture of gases, the partial pressure of a gas is the total pressure of the mixture times the mole fraction of the gas. Mathematically, we have partial pressure of gas A equals the total pressure times the moles of gas A over the total moles of the gas equals P total times the mole fraction of A. This can be a very useful tool for dealing with partial pressures of gases in a mixture. There are two problems dealing with mole fraction and partial pressure on the problem sheet for this lesson.